If you're feeding numeric data into a machine learning model, it's often good practice to pre process the numeric data so that ML models can extract the most relevant information from that data. Let's understand why this additional pre processing is needed for numeric data. Now, numeric features can represent vastly different concepts such as age, income, temperature, all of which operate on different scales and units. This diverse nature means models might treat features with larger numeric values as more important, even if they are not. The numerical span between the minimum and maximum values, that is, the range of the data, can vary significantly from one feature to another. For instance, age might go from 0 to 100, while income could range from thousands to millions, leading to disproportionate influence on algorithms. Just because income ranges are higher doesn't mean that income is a more important feature than, say, age. Now, not only do ranges differ, but the central tendency, that is the average, and the spread, that is the variance of each numeric feature, can also vary greatly. This disparity can cause algorithms that are sensitive to scale, like gradient descent based algorithms, to converge inefficiently or give undue weight to features with larger variance. When features have different scales, ranges, averages, and dispersions, directly comparing their magnitude or contribution to a model becomes challenging and misleading. Scaling brings them to a comparable level, making it easier for algorithms to process them efficiently and for humans to interpret their relative importance. In short, for all of these reasons, machine learning algorithms typically do not work well with numeric data at different scales. Now, I should mention a little bit of nuance here. Not all machine learning algorithms require features to be in the same scale. There are certain algorithms, such as decision trees, that can work well with data at different scales. But for most algorithms, it's important that you scale numeric data or standardize numeric data before using it. There are two ways in which you can pre process numeric data. The first is scaling. This technique transforms the original numeric feature to a fixed range, usually between 0 and 1, by subtracting the minimum value and dividing by the range of the feature. This is useful when you want to preserve the relationships among the original values while ensuring all features have the same scale. Another technique that's used is standardization, also known as standard scaling or Z score normalization. This method transforms data to have a mean of 0 and a standard deviation of 1 by subtracting the mean and dividing by the standard deviation. So, after standardization, your feature values are represented in terms of Z scores or number of standard deviations from the mean. Let's discuss why you might choose to pre process your numeric features using scaling techniques. Many machine learning algorithms, especially those that calculate distances between data points, like the k nearest neighbors algorithm, can be heavily influenced by features with larger numerical ranges. If one feature is measured in thousands and another in tens, the larger feature might unfairly dominate the algorithm's decision. Scaling equalizes the contribution of every feature and mitigates the influence of large numeric ranges in data. Many machine learning algorithms, like some regression models and neural networks, learn by making small adjustments based on errors. Unscaled data can make the learning process slow and inefficient. Scaling improves the performance of such ML models. One common way to scale data is normalization, also known as min-max scaling. This technique transforms your data so that all values fall within a specific range, usually between 0 and 1. It does this by subtracting the minimum value and dividing by the range, that is, maximum minus minimum. This is useful when you want to ensure all features contribute equally to the model, regardless of original scale. Now we'll turn our attention to another pre-processing technique for numeric features, and that is standardization or standard scaling. This technique is also known as Z-score normalization. It transforms your data so that every feature has a mean value of 0 and a standard deviation of 1. And this is achieved by subtracting the mean of each feature from every data point in that feature and then dividing by the feature's standard deviation. Standardization can implicitly make certain machine learning algorithms less sensitive to outliers compared to unscaled data. Because it scales values based on the standard deviation, extreme outliers will still be far from the mean, but their relative distance to other points might be more manageable for certain models. Standardization is generally preferred when the data's original distribution is approximately Gaussian, that is, bell shaped, or when your algorithm assumes normally distributed inputs. An important characteristic of standardization is that it does not change the shape of the original data's distribution. If your data was skewed before standardization, it will be skewed after. Only its mean and standard deviation will be transformed. This can be important for algorithms that are sensitive to the underlying distribution of the data.